kind of fun seeing those fighters zipping around.
That would make us some too.
I followed up with Officer for Aeronautics here at NASA Armstrong. Really excited to be sharing this time of the project with you all, this update of X-57, NASA's first all-electric X-plane. Some of you have been covering this for quite some time. Some of you have been with it since the beginning. And for others, we realize maybe this is your first time coming out here to talk aeronautics with us. So in any case, welcome. We're happy to have you here during this exciting time of the project as the project moves from development into operations. A couple of things to keep in mind. PAOs, you all, I think most of you already know Kevin and Leslie, but PAOs, if you could raise your hands, and Jess too. So, and Alex in the back there as well. So we're here to accommodate what you guys need. If you have questions or requests during your visit to NASA Armstrong, come to one of us and we'll do our best to accommodate you. We have, apparently coffee is on the way, I promise. So it should be here soon. From there, another thing to keep in mind, we're taking the SMEs here from a pretty busy schedule. So we ask that you please be respectful of their time by keeping questions during the Q&A focused on X-57. So after the press conference is concluded, we will head over to our research aircraft integration facility where we will get a look at X-57 Mod 2. As I stated, this is a busy time of the project. It is very likely that you will be seeing the ops team doing work on the aircraft when we go see it. We'll get a brief overview of what's going on in there, and you'll have opportunity for B-roll and whatever photos you're looking for while we're there. It's a lot of space there, so you guys all know the drill. Just give each other space, and we have plenty of time, so you'll get the shots that you need. After that, we're going to head upstairs to the X-57 simulator. Ringo is going to give us a demonstration in the simulator, and then after that, we will open it up. And if any of you want to take a turn in the sim, we'll give you a few minutes in the sim. If you think that'll be a good shot for you guys as well, we'll put you guys in the seat. From there, we'll open it up to interviews. So with that said, I'll go ahead and introduce, we'll start on the left, Mr. Brent Cobley.
Good morning, everybody. Thank you for coming out. As Matt said, it's a pretty exciting time for us to finally have our X-57 vehicle here on site and getting us moved into that final integration testing phase so that we can hopefully get the airplane ready for flight later this year. So I think one of the big questions is, this is our NASA's first all-electric X-plane, and really the first piloted X-plane in something like a couple of decades now. So why is NASA Aeronautics interested in this pursuit? So they started becoming more interested in electric airplanes, half a dozen years or so ago, and that interest is increasing pretty rapidly as you're also seeing the same kind of interest in industry. So electric airplanes have the promise of greatly increasing the efficiency of airplanes, and when you're doing that, when you're burning less fuel, you're also, of course, emitting less, so there's a benefit there. And then electric airplanes also have the potential to enable some really new markets for aviation, things that don't exist today, new transportation modes that don't exist today. And so I think that that's a really key thing. In some of those transportation modes, the electric actually helps reduce noise as well. So for example, urban air mobility is becoming a very exciting new market out there. There's literally dozens of companies out there designing vehicles for urban air mobility. And the way that market could be served today is with helicopters. The problem is helicopters are both very inefficient, costly to operate, but also very, very noisy. And you can imagine a city like LA with hundreds and hundreds of helicopters flying over it, people are going to be in an uproar. Electric airplanes have the potential to solve that problem. So electric is a big deal. And so a lot of money is flowing into urban air mobility. Well, let me just first say, so one of the other benefits of electric airplane, I mentioned enabling new markets. A couple of the big markets that people talk about is one, in this country, there's over 6,000 airports. But how many of them do we actually use for commercial service? It's like a few hundred. And so there's a reason for that, is the economics of smaller feeder airports and the configurations are just too expensive to operate. And so you need to go to bigger size airplanes where you can get the ticket prices down for most people to be able to fly. And so many of those airports go unused. So electric airplanes have the potential to change that economic model and be able to build airplanes for sort of short haul, smaller communities and make it economically viable for a company to operate electric vehicles. The other market, the one that I mentioned earlier, urban air mobility, is really all about, people equate it with like air taxis, the ability to use that third dimension, the vertical axis, to be able to move people around large metropolitan areas and other areas as well. And so that's a really big interest area, and X-57 is sort of aligned with both of those new markets, but especially the urban air mobility market. So if you take our airplane and you remove the outer skin of the airplane and just look at the guts of it, what you're going to see is the X-57 has the same sort of internal configuration as almost all of the urban air mobility type vehicles. It has a combination of electric systems from motors, controllers, batteries, and other systems that really make the heart of that system. So what we're trying to do, what our focus is not to create a new vehicle type. NASA's not in the business of trying to create a new configuration that an airline would go try to build and use. That's really for industry to do, and there are, as I mentioned before, dozens and dozens of companies and hundreds of millions of dollars flowing in to actually build those new configurations. So we're not in the business to compete with that. We're in the business to fill the holes. Where does industry need help in enabling this new market? And one of those areas, one of the big areas, is in how do you build this airplane safely in such a way that you can certify it in a way that we can have an airplane that's as safe as we typically are used to expecting from our aviation industry. Aviation is a very safe way to travel, much safer than driving a car, and so this new market needs to be able to meet with that expectation. We need to be able to build vehicles that are safer than driving around these metropolitan areas, and that is a very, very challenging thing to do. So our focus on X-57 is about learning the lessons of how to bring these electric systems together in such a way that we can learn about them, learn the challenges with them, and be able to develop how do we certify that. Now, of course, we're going to use the NASA airworthiness process to do that, but we have to basically go through all the same steps to prove to ourselves that it's safe enough to go out and fly this vehicle. And we're currently working with the FAA and industry standard groups right now, like ASTM, to take our lessons learned and feed them into the next generation of regulations about how do you build electric vehicles. So I'm going to turn it over now to Sean, who's going to tell you a little bit more about the aircraft and the systems and how we're getting it ready for flight.
Yeah, so I'll take some time here. I'm the principal investigator on the project, Sean Clarke, S-E-A-N-C-L-A-R-K-E, so both spelled funny. Some of the technologies we're using that Brent described, we're exploring in this initial phase in the vehicle that you'll see today, but some of them come a little bit later, so I just want to introduce some of those technologies a bit. We'll talk a little bit about distributed electric propulsion is a technology that you'll probably hear us use, DEP. That's an opportunity where you take electric propulsion technologies like motors and distributed propellers and find ways to optimize the airframe or the mission or the vehicle performance separately than just providing thrust. And so we've got features like that built into our aircraft, and we'll certainly be talking about that. A lot of those features are very similar to what you'll see for urban air mobility markets or for electric thin-haul optimized aircraft. So X-57 has a lot of opportunity to lay groundwork for technology development that applies to vehicles that look like this, but also ones that look very different. One of the reasons we're using this technology, the way we're applying it, is to demonstrate a cruise energy reduction. That's one thing this technology can do for you. So in the final configuration, our vehicle can cruise at a energy usage level at about 1/5 of what it would take for the baseline vehicle. So we're able to drastically reduce the amount of energy required during cruise flight. In order to get to that final configuration, we've got a series of modifications, we call them. So I think we've got some pictures even, we can talk through it. So Mod 2 is the vehicle you'll see today, where we've got our electric system integrated in the vehicle. It's an electrified aircraft, basically. So we'll put our high performance batteries and motors and inverter system, the motor controllers, in the vehicle, but in the original configuration. So on the original wing, inboard, near the fuselage. And this is a configuration that lets us explore the reliability and the airworthiness of these technologies in a safe configuration. Once we've demonstrated some flights with this Mod 2 configuration, we'll switch to Mod 3, where we take the aircraft and put our high performance wing that we've designed with our contractors onto the vehicle. In that configuration, we keep the same batteries and the same motors and the same propellers, but we move the motors and propellers out to the wingtips, which is a much higher performance configuration, but it's a riskier configuration. It's a harder to control configuration, and Ringo will talk a little bit about that later, I expect. That's a cruise demonstration only. It doesn't demonstrate some of the distributed propulsion effects that are most relevant to industry, and that's where we get to Mod 4. So in Mod 4, we have a high lift propulsion system that doesn't primarily provide thrust, it provides a lift effect. So it's almost like active flaps. It's a system that the pilots can use to generate extra lift when they're in a low speed envelope, and that allows them to recover the landing and takeoff performance of the original Mod 2 vehicle, but still maintain the massive cruise benefits. In order to get to this configuration with the advanced technology in Mod 4, we had to do some technology development. So our motors and controllers that we're flying in Mod 2 required some serious development, and we're still going through some of the final stages of that now. And then the battery system also required a lot of effort for us to develop a packaging system for our batteries that would be safe to put in the aircraft with our pilots. So we can talk a little bit about that, and you'll see some mock-ups of the batteries installed in the aircraft today. A lot of these technologies are similar to what are on the marketplace today for automotive vehicles, but a lot of them have to be re-optimized for aircraft. And so a lot of the challenge here has been to take battery technology and get it into a configuration that's light enough and reliable enough to fly, or to take the motor controllers and get them into a configuration that is effective for aircraft. So there's a lot to talk about. I'd be happy to answer your questions as we get into the Q&A, but I'll turn it over to Ringo.
Hello, Wayne Ringelberg, go by Ringo. I'm the chief pilot here at Armstrong. I'm also the second pilot on the X-57. Our lead pilot on this, Tim Williams, will be joining us later. Speaking for Tim and I know that we're both very excited to be pilots on the first crewed X-plane for NASA for several decades, so we're very excited about that. I have a little bit of a story to tell. When the previous chief pilot told me I was going to be on this project, he was going to relay to me why I was selected, and I expected to hear a lot about my precise flying skills and my exceptional technical background. And what he said is, no, you and Tim are my two lightest guys. It's a pretty small airplane. I don't know whether they're going to have a weight problem or not, but you're my lightest guys, so you're on. Anyway, fortunately, we do not have a weight problem, but I'm very excited to be one of the two pilots. So. Tim and I have been involved since the beginning on the project. We flew the Mod 1 baseline aircraft, which is basically the stock Technam with Rotax internal combustion engines. We gathered some data on that. We've been assisting with the development and advising on the development of the aircraft. Our primary focus, though, has been with the flying qualities of the aircraft and working in the simulator with the flying qualities team on how the aircraft's going to handle, specifically when we put the new wing on. It does change the handling qualities a little bit. Sean did mention that with the cruise motors, the big motors out on the wingtip, that does create a bit of a more challenging airplane to handle in an engine out situation. As we move into operations, we'll be working on the ground and flight test planning to make sure how we're going to check everything out before we go to flight, make sure that we can gather all the data we need to prove our research goals. We'll also be moving into pilot and test team training, where we're going to basically practice the techniques and the actual profiles we're going to be doing for flight. And we have a simulator, which you'll get to see, where we'll be able to simulate pilot-wise pretty good, and we want to hopefully also simulate most of the control room aspects with that too, so we can train as a team. Flights are not going to be exceptionally long, so we need to be very efficient. So we'll be practicing every profile prior to flight. I think when the program's finished, I think the X-57 will be a great benefit to aviation, specifically in the realm of electric flight. That's all I have for formal comments. I think we're ready for questions?
Yes, we'll go ahead and open it to questions. Brent, could I have you spell your name real quick?
Sorry, I forgot to do that. My name is Brent Cogley, B-R-E-N-T, last name C-O-B-L-E-I-G-H. I'm actually not the project manager for the X-57 itself. I'm project manager for a portfolio project that includes X-57. So my title is actually project manager for flight demonstrations and capabilities project, of which X-57 is our biggest flight project under that.
So we'll open it up to questions. If you have a question, go ahead and raise your hand. We have runners with wireless mics. We'll bring it to you. If you can, we'd ask you to identify who you'd like to address the question to. If you don't, I'll pick one for you. And also, for sound's sake, please, again, keep the mic about 3 inches from your mouth when you talk. It's really going to help our sound guys out. So, yeah, Rob.
Rob Hayes with Channel 7 in LA. Why propellers? Why not jets in a plane like this?
Sean?
I guess that's me. So I'm the principal investigator on an electric airplane, so they put an electrical engineer here. So I'll preface it with that. For aircraft of this size, propellers really are a lot more efficient, and it gives us a good platform to demonstrate the opportunities for electrification to provide an apples-to-apples comparison. So the original aircraft had a propeller about the same size. It was actually a little bit bigger, and we switched to a slightly smaller one with a similar configuration on the blades. But by showing the same propellers on the same wingspan, we're able to demonstrate apples-to-apples comparison of the original aircraft efficiency with our new electric propulsion efficiency.
Questions, Guy?
Yes, good morning. Can I just, I'm not sure who would be best to answer this one, but could you tell you what the status of the Phase 3 wing is now, and also where you are with acquisition of the lift motors as well? Thanks.
Well, you can probably cover the lift motor better than I. So the Mod 3 wing is in very, very good shape. We finished fabrication of the wing. It was brought here to Armstrong to go through ground testing. So we've already completed our static load testing, where we tested to 120% of its design limit load, and that was completed about a month or so ago. And we've also done structural dynamics, a ground vibration test of that wing as well, and it passed both of those tests. We did ultrasonic inspections of the wing. It's an all-composite wing, before and after both those tests to ensure that the wing is in great shape, and it passed with flying colors. So very shortly we're going to be shipping that wing over to ES Aero. We haven't mentioned ES Aero yet. ES Aero is the prime contractor that we're working with. They're in San Luis Obispo. And ES Aero is going to integrate that wing, do some of the integration for Mod 3, and do an integration with they have a spare fuselage there, and do the integration with how the wing is going to attach to the fuselage. So we're going to have to modify our flight vehicle later to be able to take the Mod 3 wing. And maybe cover the high lift one.
Yeah, so for the high lift system, we started on that a little bit later than the original project. So that part of the project is actually in the design review cycle. We're actually doing our critical design review in 2 weeks on that system. We've got prototypes working. We've done some wind tunnel tests. It's actually working really well for us. We've got a motor controller developed with technology that NASA has developed in-house at our Glenn Research Center. So we'll go into fabrication of the flight units in the next couple months after our final design review in 2 weeks.
Deal with the weight of batteries, and how do batteries compare to fuel weight-wise in a situation like this?
Yeah, batteries are a challenging technology for this aircraft. We didn't set out to explore aircraft batteries. That's not the goal of the project, but we needed batteries in order to meet the goals of the electric motor integration. Our battery system is about 850 pounds on the vehicle, and the whole vehicle is about 3,000 pounds, so it's about the third of the vehicle weight. And we actually spent a lot of time optimizing the batteries for safety features that weren't available on the market. I'm not sure where else to go with your questions, so let me know if maybe you have a follow-up.
Just add a couple of things. You know, one of the other economic benefits of electric is the maintenance cost. So when you have a fuel-powered engine or turbine or whatever, you know, there's a high cost in terms of maintenance for those things. Where electric systems are expected to have much lower maintenance costs. So that's a player in some of the new designs. You would never see somebody put a fuel-powered 6 or 7 motors on an airplane, because the maintenance cost will kill you. But you could put one power system, one battery system, or some kind of system that's generating power, and distribute that to 6 or 7 motors across the vehicle, and come up with a much more optimum design. So a lot of these urban air mobility vehicle designs you're seeing are optimized in having multiple rotors on the vehicle, which provides redundancy if you have some fail. It potentially allows you to operate much quieter. So it has a lot of benefits. It just basically gives the engineers a couple extra degrees of freedom to design something that's totally new, and you're seeing that out there on these really crazy designs that are coming out.
Quick question for Ringo.
Sure.
How different is it to fly a plane like this with that many propellers compared to a standard aircraft? And what kind of training would be needed for a pilot to pilot something like this?
Right, so that's an interesting question. The implementation that we're using for the high lift device is primarily, like Sean said, just to provide high lift. So we're really operating them like flaps. So from the standpoint of physical operation of them, they'll be fairly easy. You turn them on, like you put your flaps down for takeoff, and then you turn them off when you no longer need the flaps for takeoff. When you start talking about failure modes and the ability to monitor failures, obviously you have 12 motors out there, so a little more to keep an eye on. So we're looking at ways to just have like one indicator for the pilots instead of 12. So those are all kind of things that we're working with. So I think from the standpoint of a failure mode, it might get a little more complex, but certainly in this implementation, it's fairly easy. They're not throttled by the pilots. They're all automatically controlled based off of airspeed is how they're scheduled. There can be many other implementations that could get a lot more complex from a control standpoint and likely be handled by computers with simpler inceptors for pilots is my expectation.
And then Rob, you asked about the training as well, right? So maybe you could talk a little bit about the simulator, what you've been doing there.
So the simulator, I mentioned a little bit in my opening comments. Simulator has been used for handling qualities, flying qualities evaluation, and for a little bit of training up to now, but it'll start being used a lot more for training. So we'll rehearse every flight in there. And we've been looking at failure modes in the simulator as well. So different types of failures of particular channels of the electrical system and how that affects the high lift motors and how that affects the way the airplane reacts. Some of our initial analysis on it thought that it would be fairly dynamic with longer half of the high lift motors on one side. When we did in the simulator, it did not seem as dynamic as we had initially thought. So it's a great tool to try and see what the actual reaction times and how you would respond to it and how controllable it may be in those kinds of situations.
Questions? Gene? Just
Good morning, Gene Kang with NBC4. You know, maybe I'm being a little bit of a simpleton here, but I know people are used to, you know, like when a Tesla or a Prius pulls up on you and you have no idea because it's so quiet. You talked about noise pollution. Can you talk about the implications of that and what this will do for the future of aircraft? You touched upon that earlier as well.
I mean, I think, especially in the urban air mobility market, where you're talking about, you know, tens, hundreds, maybe even thousands of vehicles flying over a city. If they're not quiet, that market's not going to exist. The public's just not going to, you know, accept that. And so, to me, it's an enabler. It's an enabler for the technology. You just can't do it without that. So that's a key. It's a key enabler for the whole new market coming in. So I'm not sure. That's one aspect of your question. I don't know if you want to follow up with.
Yeah, I mean, overall, you know, for example, people think about ground transportation, and so not everybody has an electric vehicle. So
right.
This obviously is in testing phase. Just going forward the next maybe 10, 20 years, will this be the future of aircraft? Will it now be all electric?
Okay, so I think electric has the potential to enable some new markets like we talked about, and then it has the potential also to improve existing markets. So it's sort of in its infancy now because we're starting small. We're starting in sort of the 1/4 megawatt size power. But when you start talking about bigger, you know, commuter airlines and full-scale single-aisle type airplanes with hundreds of people on them, right now there's no battery technology on the horizon that can power a vehicle like that. So you're going to have some combination of, you know, fuel power engine combined with some electric system. So like a hybrid. So it's not that unlike a hybrid car. Adding electricity to a gasoline-powered engine, the combination, you can do some design trades that makes it more efficient, get you better gas mileage. You can do the same things with bigger airplanes, and so that's sort of the next step for electric. Is there's already people working towards larger airplanes. A lot of the big companies are starting to investigate doing those trade studies now to look 20, 30, 40 years out. The stuff we're talking about now, the smaller scale vehicles, are much, much closer. 5, 10, 15, 20 years, certainly within our lifetimes, to see operations happening on a regular basis. So I think it's pretty exciting. The short-term stuff we're doing, I think, is super exciting. The long-term stuff is further out, but I think it has a lot of promise to improve efficiency. And even a few percent efficiency in the aviation world is a huge benefit. And the potentials are more like 10% or more in the big airplanes. Where in the smaller airplanes, you already heard him talk about 5 times energy reduction, using 20% of the energy. It's a huge change to the cost. You add maintenance costs and operations costs to that, and you now have a market that couldn't exist otherwise without electric vehicles.
And I'll just go back a little bit to so the noise level for these vehicles will need to be a lot lower than helicopters, say. We don't know what they're going to sound like, and that's part of the benefit of X-57 is we can start to learn about how these technologies sound when they're deployed on an aircraft. It's easy for us to model an electric motor in a lab or away from an airplane, but when you put it on a wing and it interacts and the sound bounces around, and what does it really mean to a surrounding community? We'll get an early look at that. This vehicle's in a different configuration than what you might see flying around a metropolitan area, but it's a useful baseline for us to update our models and understand what the challenges really are.
Yeah, Guy. Just. Oh, sorry. Sorry, Guy.
All right. We'll go with the bigs, Guy.
Got to be quick. For those of us who have electric vehicles at home, a big concern is charging time. How long would it take to rejuice this thing?
So our battery system is 800 pounds, I mentioned. The amount of energy we can store there is not as much as you could store if you were using gasoline or a hybrid system. We'll probably be able to fly for 45 minutes or so. So if you empty the battery in 45 minutes, you could probably charge it up in 20 or 30 minutes. We're not planning to do that. We don't want to stress our batteries out because there's no need for us to be turning around and flying again in half an hour. So for us, we're going to take our time. We're going to charge it over about 5 hours. But the battery technology, if you implement the cooling and the system management, then it's certainly possible that you could do rapid charging like you see in some of the automotive platforms.
And just real quick, a non-technical question. How cool is this airplane? I mean, what do you guys think when you look at this and you have designed something so odd looking compared to other aircraft?
I don't know. I kind of want to hear what Ringo says.
It's definitely a unique looking airplane for sure. It's a general aviation airplane, so there's a very strong general aviation community out there. So I think a lot of people will be excited about that. Something new in the general aviation realm. For Tim and I mean, we're just excited about the new technologies that are in it and the team that's been involved getting it ready. So we are really looking forward to flying it. And I'm going to feel just as cool in that as I do in any other airplanes I fly here. Or more cool. Probably more cool.
I'll show a little bit of my age here. I'm one of those people that grew up watching lots of cartoons, and to see the era of the Jetsons actually being something that's potentially real is pretty exciting. I think it's cool.
Yeah, and the technologies are just amazing now. So you can flip a switch and the motors start up, and when you've got lots of little motors running, it's a completely different feeling from having little piston engines or turbine engines going. The sound is different. It's a higher pitch but less noisy sound, and so just being able to take these technologies and actually apply them in a useful way to the aircraft is really exciting.
Guy Norris.
Just a quick follow-up on the flight testing, probably for Ringo. When you're looking at failure scenarios and asymmetric control conditions, can you sort of describe what the difference will be between phase 3 and 4? Because if I understand it correctly, an electric motor will have multiple failure potentials, but on the other hand, you'll always have that backup provision to be still making thrust, because it will be more than one motor per propeller.
Right. Yeah. So I think the biggest handling qualities change we're going to see from a failure standpoint is going to be from Mod 2 to Mod 3. So Mod 2, as you may recall, is the stock Tecnam airplane with electric engines on it. So the handling qualities of that airplane should be almost identical to the Tecnam. Our CG is a little further aft than the stock airplane, but within limits. So it's a little further aft than what we flew when we flew the Mod 1 stuff. But the big change from Mod 2 to Mod 3 is moving the motors out to the wingtip. So now when you have a failure, the airplane, the stock airplane from a thrust standpoint is not really single engine capable. I mean, it depends on where you're at. You might get lucky, you can maintain level flight, but it's a standard light twin, you know, reduced climb rate when you have a engine out kind of situation. So, but from a dynamic standpoint, loss of that outboard engine is pretty dynamic. So for Mod 3, we'll be flying without the high lift system for takeoff. And then for Mod 4, we'll be employing that for takeoff. So the takeoff speeds will be a lot quicker for Mod 3 because we'll be not relying on the high lift system. So we'll have to basically take off roll a lot faster before we lift off. And that's also going to be helpful in a failure situation because the more speed you have, the more controllability you have if you lose a motor. The redundancy in the electrical system is pretty good. Do not expect an electrical failure that would take out a whole motor. It would only take out half, which is very controllable. A loss of a whole motor is a pretty dynamic situation and requires quick pilot response.
Right, and just a quick follow-up, if I may. More for you, probably, Sean, in terms of the program. How long do you think the Phase 2 flight test effort will take, and when do you expect Phase 3 to begin, or hope?
Yeah, that's a good question. So we plan to fly Phase 2 next year. The time and the schedule for flying Phase 2, Mod 2, is we've got a couple months book kept, and there's a dozen or so flights where we'll study different aspects of the system. And so we've got detailed plans for that. And then Mod 3 will turn around very quickly after that. So in parallel to that Mod 2 testing that we're doing over the next 6 months or so on the ground, and then the flight phase at the end of next year, we're developing the wing systems, like Brent mentioned. The wing is actually here and getting ready to go back and get those systems integrated onto it. And then the Mod 4 systems will be going into fabrication in a couple months, and then we'll be doing the qualification and acceptance testing on our new motors, on our 5-bladed folding propellers that are custom designed. So there's lots of challenges there that we're looking forward to. So there's a lot going on all at once, and we plan to turn around pretty quickly after Mod 2 and get those new technologies into flight.
Suppose the plane was in operation today. How long would it take me to get from here to LAX?
Who's got a good guess at that? Yeah, so our cruise speed is about 150 knots at our highest test point. The system wasn't designed for range, so I always have to caveat. We didn't put enough energy on there to fly for very long distances because we're going to land right where we took off, and we didn't need to. But the system is about the same flight speed as the original Technum and about the same envelope, but we don't intend to use the full altitude capability.
So it's not faster, but it'll be a lot cheaper.
Yeah.
to get you there.
But still, how much time would it be? Would it be an hour? Would it be?
Probably 45 minutes. Well, up here to LA, dealing with the traffic, it's probably going to take you longer than driving. But traffic as in
With air traffic.
The air traffic. So it's probably, straight away, it'd probably be a half hour, maybe 45 minutes.
But we should go to Vegas.
It's probably a little over an hour.
Yeah, we've been talking a lot about urban air mobility, which is vertical lift type vehicles that use these technologies. But in my opening statement, I was talking about sort of these short haul kind of vehicles. So we're talking about when you go to on a normal airplane, it seats 100 to a couple, 300, 400 people. But there's this missing market, right? From if you're in a small community of 100,000 people and you're remote and you have to drive 5-6 hours to the big airport, it'd sure be nice if you could jump on an airplane with 20 or 30 or 40 people and take a commuter hop over there and not have to drive 5 hours and get there in an hour and 15 minutes. So that is a big potential market for electric vehicles, because now you can make those costs much cheaper so people can afford those tickets. Because if you put 20 people, 10 people on a vehicle today with the motor maintenance and fuel costs and all of that, the cost of the pilots and crew, the costs are just too high. The ticket price, nobody will buy them. And you've seen airlines try to start those services. We had one here in Palmdale, right? United Airlines was here for a while. Couldn't make it work. Even though we've got several 100,000 people in the valley, couldn't make it work. So that is the big potential for that field of vehicle, is opening up some of those 6,000 airports, so we can basically bring better mobility to a lot more people, not just the people that live, a few 100 miles from a major airport.
Stephen?
Hi, I'm Stephen Mayer with the Bakersfield, California. I hope this isn't redundant, but Sean, you talked a little bit about, in very technical terms, some of the difficulties of driving this plane once the wingtip motors are installed. And I'm trying to put myself into the seat of the mind of a general aviation enthusiast, and there's a lot of them out there who are going to be interested in the handling or how this plane flies and the difficulties of moving the motor to the wingtip. Speak in more general terms and kind of rather than being so technical, what's it like up there, or do you have some idea of what it's going to be like up there once the motors are out on the wingtips?
I'm guessing that's for me. So in a general sense, any kind of wing-mounted twin-engine airplane has a turning moment that happens when one motor is on and one motor is off. And that turning moment has to be counteracted with flight controls, primarily with the rudder and a little bit of aileron. So when you lose a motor, it's a fairly dynamic event. You get yaw and a little bit of roll, and you counteract that, and hopefully you still have enough thrust to stay flying. As you move those motors further away from the fuselage, that's a greater moment arm, so it's going to be more of a turning moment, more of a yawing moment. So what we've found in the simulator with this aircraft is a complete failure of a motor, which again, like I talked about from an electronic standpoint, electrical standpoint, we don't expect to happen given the redundancy we have. But a complete failure, say for a mechanical situation, is a fairly dynamic event, not yaw and roll such that if you're low to the ground, you don't want to damage the airplane as you touch down on the runway. So what would likely happen in a commercial implementation or even a private, I guess, if we're going to sell this to the general public, there would probably be some type of automatic system that would help you in an engine out situation. And those are prevalent in airliners right now, so they're not very complex, and there's ways to handle those. The easiest way to counteract the yawing moment is to pull back the motor that's operating. So any kind of automatic reduction in thrust on the operating motor would be helpful. So there's some fairly relatively easy techniques, but likely something automatic would be helpful for a general aviation pilot in a situation like that. Thank you.
2 more questions, please. Going once, going twice. Okay, well, we'll go ahead and wrap this up. What we'll do now, if you want to leave stuff in here, that'll be okay. We're going to have our security folks right next door go ahead and lock the room down, so everything will be fine. If you have a news van with you, I think it's 3 of you, you'll follow Leslie Williams she'll show you where to park. She's going to guide you through the gate here, have you park near the hangar. Due to limited parking over there, the rest of us will hoof it as a group, and we'll go ahead and take a look at X-57, Mod 2. So, hang out for just a couple minutes. So Sean, we'll talk later. We'll give them maybe 5 minutes to get some shots and get the cameras set up, and then
This is the X-57 electric motor being installed where the Rotex engines used to be. It's an air-cooled engine run by battery.
That overview right now.
So like we mentioned, this is the Mod 2 configuration of the vehicle, where we've got the original Technim wing, and our electric propulsion system is integrated in the existing locations on the wing. A couple of features you can see, we've added a research air data boom to the front of the aircraft, so we've got a large probe out in front to help get us pitot and static airspeed. And then that'll be used for our performance evaluation of the vehicle. You can see on the wing, the red parts are the electric motors, so that's our cruise motors. They're rated for about 72 kilowatts for short periods and can probably do about 60 kilowatts continuously, which is more than enough with our high efficient wing to provide the flight performance that we need. Behind the cruise motors, buried in the nacelle, there are the inverter systems, and there's actually 2 of them for each motor. So the motors have redundant windings. There's 2 independent sets of windings and then 2 inverters, and then 2 different DC distribution buses that go back to the battery system. And then the battery system is in the fuselage. So there's a structure that we've designed to mount our 800 pounds of batteries in the back seat and in the cargo area of the fuselage. Right now we're installing mock-up batteries for our ground vibration test, which starts in a couple days. And so these silver boxes that the crew is taking and mounting in the vehicle are the exact same shape and size and weight of the live batteries. These are inert boxes that have mass simulators in them to simulate the lithium-ion cells that we'll actually be flying with. And so as we put those in and then instrument the vehicle with accelerometers, we can do our dynamics testing for ground vibration modeling. And that's where we'll take all the accelerometers in the aircraft and add a bunch more and look at how the system vibrates all together. And then we can learn whether our models are accurate for how the flight performance will be of the structure itself. So that's an overview of what you can see from the outside. I guess if there's any questions, we can talk about in specific features.
Can you talk real quick just about the amount of flight time you would get out of these batteries, and in terms of time instead of kilowatts?
Yeah, so our battery system for the 800 pounds of lithium-ion packages that we have, we can probably fly for about 45 minutes. That's a 56 kilowatt-hour pack if you want to compare it to what an automotive manufacturer would advertise. But our system is entirely air-cooled and passively monitored, so it's a lot lower maintenance than what you would do for a commercial application, but it's a very simple system that we're able to develop and integrate quickly.
Was adjusting for batteries versus engines on the wings, is it hard to center of gravity and finding all that stuff?
Yeah, integrating 800 pounds onto an existing airframe is very challenging because the center of gravity of the vehicle drives a lot of the performance, and so we had to be very careful about where the batteries were mounted. And also, the batteries don't move around in flight like fuel does, and so you've got to plan for the entire flight envelope. And so we had to be very careful about where the batteries were mounted and how that interacted with the flight dynamics.
These propellers don't look real big for a plane this size.
No, the propellers are a little bit smaller diameter than the original propellers, but because we've got electric propulsion system driving them, we don't lose power with altitude like you do with an air-breathing engine. And so our system actually has 60 kilowatts available all the way up to our flight ceiling. And so it changes the sizing that you would do quite a bit for an aircraft.
Have you faced any challenges with the ground testing so far, or things that you didn't foresee happening?
We've had a lot of challenges with the ground testing. One of the big features for developing a system like this is we want to be able to run our motors and our flight systems with facility power and not use batteries every day, because the batteries take a long time to charge and you got to be very careful about their thermal performance. And so we have a ground power I don't know what the word I would use, a ground power station that we can use to power the vehicle off of high voltage facility power. That introduces a whole different set of requirements than the batteries do, and so designing the vehicle for both of those configurations is a bit of a challenge.
As the motor is turning over, is it generating electricity to recharge the battery?
We can use the motors to collect energy from the airstream and put it back in the batteries. It's not a feature that we need to use in Mod 2, because anytime you do that, you'll be slowing the aircraft down and descending. But in Mod 4, when we've got the high lift system going and we want to go in for a landing, the system is generating lift like we designed, but it also generates extra thrust, and we don't need the extra thrust to land. And so we can use our cruise system to counteract that thrust and slow the aircraft down. And so that's a nice feature of the electric propulsion system, that all the technology is there, and it's almost free to get that regenerative capability, as long as you don't mind taking energy out of your flight path. Anything else look funny on the airplane that we should just explain? The crew right now is installing the battery system, so we've got 16 of these modules. Each of them are about 51 pounds, and they hold 320 of our 18 650 cells. Someone's doing very fast flights overhead right now as well, it turns out. So with 16 of those modules in the aircraft, we get about 45 minutes of flight.
You said you were asking questions about the power. Can you put it, in something that people can understand? So I do that myself. I figure out what is the calculation that people can understand. That battery can put out about the amount of power you need to power 100 American average houses. So I mean, it's a lot of power it can put out, but it can only put it out for, like you said, about 46 minutes.
And the plane is going to weigh how much total?
The stock aircraft is about 2,700 pounds. With our battery system and our integration, we're increasing that limit to about 3,000 pounds, and in Mod 4 we may even go to about 3,100 pounds.
But the batteries will weigh about 800.
The batteries themselves, the boxes that hold the lithium-ion cells are 800 pounds. There's a lot of other stuff that goes with it, so you need to have your monitoring system and your isolation systems, and with all that together, that's another 50 pounds or so.
How much does each one weigh?
Each one of these silver boxes is about 51 pounds.
With the advances in the technology of batteries and motors and efficiency, 15, 20 years ago, was this totally a dream?
These technologies were not ready more than 5 years or so ago to even imagine an aircraft in this configuration. And even while we've been developing the system, advancements in batteries and advancements in motor controllers especially have continued to advance. And so that's where it's exciting, is the technologies that we're maturing here are going to be ready to be applied to more and more architectures as time goes on.
So 5 years from now, who knows what these batteries...
Yeah, it's hard to predict the future, but batteries are getting better and better all the time.
Do you have a possible timeline, a hopeful timeline of maybe when, the general population will actually see one of these in flight after all of the testing has gone forward? We're talking 5, 10 years?
Yeah, so different architectures of vehicles could use these technologies in different times. And so for a small vehicle like this, the technology is much closer to being available. For larger vehicles, for a 15-passenger or a single-aisle aircraft that has a 300-mile range, it takes a little bit longer to get the technologies to a maturity level there. So we're helping to develop the technology, the airworthiness standards for this, but getting it all the way into a commercial context takes a lot more work.
So several years?
It's hard for me to say.
That's Nostradamus.
NASA develops the technology and demonstrates it in flight.
Metal box over there, that's what the battery is.
Yeah, so these metal boxes that say inert on the side are battery knockoffs. And each one of those can hold about 320 18650 lithium-ion cells. And when you put 16 of those together, we end up with 56 kilowatt hours of energy available on the airplane.
So we've got about 10 more minutes down here, guys, and then we'll head up to the simulator. Feel free to keep asking questions if you want, and then we'll head up, and we will give you the opportunity to come back down here afterwards and do some one-on-one interviews as well.
the box light actually turn it on.
I love it. Blue light, internal batteries next. Huh? They have an internal battery. Yes, right here. It's the balance here.
Come across that guy's right here.
You want to put a little light on it?
developmental display that we're using primarily for engineering stuff, but it's also working on some unique ways to display electronic flight characteristics of an airplane, the energy and all that kind of stuff. But given that this is kind of all developmental, we're relying on these gauges here to fly with. So we've got basically our voltage, which is kind of how much fuel we have, current, which is how much power you're putting in the motor, and this is computed power. You can see there's four, so we've got that engine right engine, and two channels on each side. That's that preventative. It's full enough there.
Sir, can you step back, please? Thank you.
So the displays over here are primarily from the stock aircraft. We did repurpose some of the annunciators for what would be electric failure ticket. Another look at the airplane, so you can see we got the 6 high lift I work right here. Turn that on. And cruise motors are on the wingtips. Takeoff with the high lift system operating. It's going to look a lot like a regular airplane takeoff. We've got RPM on the cruise motors here. I've got this light telling me that the high lift system is working. Because we got high lift working with flaps, we can rotate at a speed similar to what the stock detector did. Flight test profile, we'll be keeping the gear down because we're always worried about an engine failure. So we won't be cleaning up, but for this particular demonstration, we'll just go ahead and clean up and speed up. And eventually what we'll find is that the high lift system should schedule out. So I'm just going to kind of go around here and we'll bring it in for a landing, and then we'll see if you guys have any questions. right, so we can open it up for questions. That's not good now. That's not good.
How different is it flying something like this right now in a simulator compared to a standard?
Well, the simulator is a like for this one, what our relevance is. That's why we're focused on this. Because it's straightforward finding about what it's I know what is that the other companies are all competing in this field. So they're holding, sorry, go ahead. Yeah, sorry. So, and then one of the interesting things about NASA is we're focusing on certification of these airplanes, the lessons learned, how to come up certification agencies, come up with how do you test these airplanes, how do you design them, how do you flight test them, how do you certify them? Because right now there's dozens and dozens of companies out there competing each other. Survival of the fittest, right? There's not going to be 50 companies 20 years from now. There's 4 or 5. And so they know that. All their lessons learned, they'll share all of the parts. They'll share something. They're all really like nuggets of information. They want to share. So NASA now actually we're sharing. So when you show the certification, we're very excited. Like, we have a battery test plan, certification, and they use that as a basis for discussing what should be the battery. So that's very valid for NASA.
What you saw in the simulator, very thin wings with these small little motors out on the wingtips, giving us essentially blown lift. The ability to do that is unique because we're able to scale down the size of electric motors, drive little propellers. Very simple technology, very lightweight. The engineers, many companies as well as NASA engineers came up with this idea of doing this. And also because they're scalable and they have electric motor controllers, we can control them with software. So the whole world's based on software. We can modify it as we go, and we can make the most of this airplane. You would think, oh, you have all these lift generators, as you were. You could do such neat things in the future as modify the lift curve over the entire span of it. We haven't even talked about that, but that's a potential that we could do. We cannot do that with gasoline motors. You just can't work gasoline engines. You just can't do that. So it's pretty neat from that standpoint.
What about your biggest concern in flying this aircraft?
The biggest concern I have is what we've done is eventually Mod 3 and 4 put big, I'd say pretty big electric motors on the wingtips. And as you know, if one of those was to suddenly go out, lose power, we could develop a dynamic event. That kind of dynamic event is something that we have to prepare ourselves for. But the whole idea of doing that was to prove out the effect of making this wing, which is very, very small, making it as efficient as you possibly can. And that's the reason we do that. Actually, that's the reason we chose this platform, the Techno, because it's a high wing. There are many general aviation airplanes that are low wings. But we wanted something high so we could put these electric motors and wingtips for these propellers.
Is there anything else? Any other favorite facts or interesting things about this plane you'd like to share?
Well, the development of it is going to be such that we'll do very short flights. I mean, there's no kidding. There's something that we have to learn, and that's the battery technology. Lithium ions, as you know, that's what we're using. And when you use those at a very high rate of discharge, we have to make sure that we're not going to run it down below a certain level where battery voltage or the state of charge on the batteries is too low to bring the airplane back. The good news for this is all the profiles that we do, I just apologize I got into this late, but maybe Ringo showed you, hey, I can shut down the motors and glide in. So the idea with this airplane all along was the idea is that, yes, we have two motors on it, or maybe even more with the distributed little electric motors. And when I have any type of problem, I have a single engine mindset. I just lost my motor, I'm going to glide to a landing. And the only place I could think of that you could do that is here at Armstrong Flight Research, essentially Edwards Air Force Base with all these dry lake beds. That's really the saving grace. And what you saw up in the screen is what we were trying to show you there. So,
Sorry, go ahead.
Does this plane, you haven't really flown it yet, but the original, does it fly like anything else that you've flown or test piloted in? Without electronic, just from the manufacturer.
The Techno.
Yeah, does it fly?
It's pretty good. I mean, it's a good multi-engine trainer. Yeah. It's very efficient because it uses Rotax motors.
Yeah.
And the big fuel costs are your biggest thing when it comes to for someone wanting to learn how to fly.
Yeah.
I mean, you go out there, you have to point them thousands of dollars, and Techno, Italy, came up with a great design. Yeah. And it's excellent. And it's very, very safe. Yeah. So when I was very happy when they selected this project. How do you take off like this is, that they're all going to have to deal with it. Okay. The other one is state of charge on the batteries, because we're all using lithium ion currently. I mean, there may be down the road fuel cell technology, other ones out there, and we expect that the energy source that we have out there will improve over time. Right now, lithium ion is where it's at in terms of how much energy you can have for the weight. For pure electric, okay? That's what I know of, and eventually maybe fuel cell.
That's it for me. Anybody else?
Any other?
I guess the one question would be, how long is it going to take to prove it out, to fly it? And is it going to take 2 years, 3 years, 4 years? No.
That's a great, excellent question. Not to say your question's but I'm saying is, when we do this technology, the commercial markets are right behind us.
Yeah.
And if we wait too long, they're going to go past us. And why should we continue if the commercial market's already doing more? They've already figured it out. So what we're trying to do at NASA is trying to figure out the hard stuff so we can give it to the commercial market.
Yeah.
And make it so that technological hurdle, we've already done it, you can take this and use it. One of the things that we figured out was there's a term, and well, I won't use the term so much, it's if you have lithium ion cells, let me ask you guys, in lithium ion cells, you take a lithium ion cell, typical, and you expose it to 100 degrees Celsius, boiling water. Just drop it in a pot of boiling water. Should you run away? Yes or no? You should run away really quickly.
Okay.
Okay, that's a bad deal.
Why does it explode?
If they get too hot, water's the one issue because it's conductive and it'll short the battery. But the other part of it is it gets too hot, and those cells are going to take off. And they produce so much heat that they can actually take their neighboring cell, and that's why this design is, they can propagate the heat to that next cell, that takes off, and the whole battery pack is a mess. Okay?
Yeah.
I don't want that. So they designed on this airplane where you can have a cell that would be, for whatever reason, take off, and it's not going to propagate that heat to the neighboring cell.
Okay.
And we don't use a cooling element like water or anything like that. It's just purely, when it's made it as light as we can. That's the key one. If we're going to use lithium ion, you have to design so you don't have propagation problems of one bad cell.
Was that what happened to the Dreamliner?
There's a potential. I don't know enough about it.
Yeah, I don't.
But the knowledge base of what I've learned in just the last couple of years with lithium ion is this is a mindset you have to have. If I have a cell in an array of cells, how do I design it so that that cell does not put so much heat to all the neighbors?
Yeah.
And then you have to prove it, and you prove it by putting it out there and do it.
Yeah.
So NASA has done that. I mean, you can imagine lithium-ion cells on people who are out there on the space station, out there, and they've got packs on the back. They've got to figure out how to do that right.
Yeah.
And we take some of that technology, borrow it, and put it in an airplane like this.
Yeah.
So you asked earlier, Jesse, hey, what's the thing that probably worries you the most? It's not the batteries. It's not. Because we figured out how to do it, and then we tested it.
Yeah.
So one cell cooks off, it didn't propagate to all the others.
I see.
It's one little hurdle after another. That's what this plane's all about. So when I go fly, but there was so much that had to go on before then.
Sure, but now you're going to be with this program.
I would give
2 or 3 more years. You'll have it proved out.
2 or 3 more years. We're hoping to do this with this wing, and then we'll test it, and then there'll be a point where, hey, stop testing, we bring the plane down, take that wing off, put the new wing on.
Yeah.
You know, integrate everything, make sure everything's working.
Yeah.
We fly the new wing, just like you saw in the sim.
Yeah, got it.
That'd be very cool.
And that must be the new wing over there.
It is.
It's actually more than that.
Oh yeah, most of it.
More dense. It's 40% the forward, a little bit less span, but it weighs more than the original. And so we'll have a high lift part down here, and then the next one is here, and the next one is here, and then we'll go so they're just spacing pretty close. The flap system here, and the aileron system here. And then on the leading part of the wing is where we've got a high lift power system and instrumentation system. So all the power wiring goes through these conduits that snake all the way through the wing. And then these round holes are actually for instrumentation conduits. We're going to have a data acquisition system that'll have sensor wires running through there, and then they can pop out into individual high lift nacelles or go all the way out to the cruise system in the wing.
So is the wing composite?
It's a fully composite wing. It actually has a main spar that's also composite, carbon fiber, and then a trailing and leading spar. And the main spar doesn't attach to the fuselage. Ribs take the loads from the main spar, transfer it to the trailing and leading spar, and those attach to this H-frame structure, we call it, the aluminum structure there, and that's what attaches to the fuselage. So it provides it's almost like glider wing is what I've heard it described as. It's the structural configuration is similar to how you would design a high aspect ratio glider wing.
Sure, sure. And the big engines go
out
on
at the wingtips. So there'll be a nacelle that's about 6 feet long.
Oh yeah, wow.
Yeah.
More.
Yeah, well, sits here, but then about 3 feet that way and 3 feet that way.
Oh, wow.
So the engine, the red motor will sit right here, and then the prop will sit here. We'll have our motor controllers and then instrumentation sitting right behind it. And so there's actually another conduit, just like this one, that is a straight shot from the wingtip all the way down. You can actually see it there. It's kind of dark, so it's not going to be a good picture. But that conduit carries the 72 kilowatts that you need to get out to the cruise motor.
Was this designed at Langley?
Langley did the aerodynamic design. It was based on the Leap Tech experiment that we had done, so it's a similar airfoil that was optimized for this. And then ES Aero and a company called Experimental out in San Luis Obispo did the structural design of the wing.
Can I ask you to put this mic on?
Sure.
Here's the, you can put that in your pocket or whatever.
Okay.
Yeah. Just put that